The second degree expression, 5x squared plus 3y squared plus 3z squared, with the cross terms minus 2xy plus 2yz minus 2xz, and linear terms minus 10x plus 6y minus 2z, all equal to 10, well, that amounts to a rather long equation representing this ellipsoidal surface. Well, the equation can be reduced to this standard form, which is achieved by a suitable isometry to change the axes. Of course, now we'd be working with a new x, y, and z. The isometry is such that we want to lose all the cross terms, those in xy, yz, and xz, and also the linear terms. So we're left with just the terms in x squared, y squared, and z squared. Well, you'll see the details of this algebra in your text, but what it actually does for you is implement an isometry that does two things. First of all, the isometry rotates the axes, and then it translates them so that the axes become central. Now, it's fairly easy to see what this means in terms of the algebra. This is the rather horrible equation that we started off with, and it can be written somewhat more succinctly in matrix form. Now, the first thing we recognize is that we have a symmetric matrix, and we know that can be diagonalized by an orthogonal transformation. Now, that corresponds exactly to the rotation that we did of the axes. Well, when we do that, we find that here's our diagonal matrix, and we still have these linear terms. And then what we can do is we can translate, that's what we did the second bit, and we can lose the linear terms. Don't forget, that won't change these coefficients here, but it will change the constant. And then we can rewrite the equation in this nice, simple, standard form. Of course, the x, y, and z now refer to the new axes. Well, given this standard form, it's fairly easy to see what sort of surface we're dealing with. Well, let's see why that's the case. Well, if we look at our equation, then in this form, I say it's an ellipsoid. Because let's take a fixed z equals k. But geometrically, that means we're just slicing by a section z equals constant. Now, we can rewrite the equation, and it has this form. Now, for a very large k on the right-hand side, we'll have a negative right-hand side, and the left-hand side is always positive, so that's just nonsense. But for moderate values of k, when the right-hand side is positive, then you'll recognize that this is the expression for an ellipse. So slicing by a plane parallel to the xy plane gives us an elliptical section. And it's fairly easy to see what's going on by means of a model. Well, here is our quadric surface, and you'll recognize it's precisely the one that we had at the beginning of the program. It's an ellipsoid, and if I take a slice with z equals constant, that corresponds to a plane along here. Now, if I take very big z, that's way up here, and, well, I won't get anything at all. That corresponded to the right-hand side being negative, and I don't get any curve whatsoever. But if I take a slice about here, then what do I get? I have a nice ellipse. And if I take a slice here, that's another plane parallel to the xy plane, I'll get a bigger ellipse. In fact, for the various values of k, I'll get a whole series of elliptical sections. And actually, it's fairly easy to see that if I take a y equals constant section, that's a plane parallel to the z plane, then I also get an elliptical section. This is another parallel plane. I also get an elliptical section here. And if I take an x equals k, that's a constant section parallel to the yz plane, then I'm also going to get an elliptical section. So all sections parallel to these three coordinate planes are ellipses, and what we have here is called an ellipsoid.
Well, in general, we're interested in equations like this. And as you've seen, we can rewrite it a little more neatly using this symmetric matrix. And of course, because the matrix is symmetric, then we can diagonalize it by an orthogonal matrix. And if we're lucky, we can also remove the linear terms. And that will leave us with another constant. So the final form of the equation is like this, and that's just a generalization of what Alan showed you before. He dealt with the case when all three coefficients were positive, and so was the constant on the right. Notice that if the constant here had been negative, then we'd have no real points at all on this surface. Well, for the remainder of the program, we're going to investigate the various possibilities that arise when we change the sign of some of these coefficients, but we keep the constant positive. So let's start by keeping A and B positive and changing C to make it negative. So we might get an equation like this. A is plus 3, B is plus 2, and C is minus 3. Well, what sort of shape is that? Well, to find out, we can use the technique that Alan was using. We can cut a slice through it. We could try, for example, a slice parallel to the xy plane, and that means a constant value of z. So let's put z equals k and rearrange the equation to get 3x squared plus 2y squared is 1 plus 3k squared. Now, I think you should recognize that that's the equation of an ellipse. And furthermore, it doesn't depend on the value of k. Whatever section parallel to the xy plane we choose, we get an ellipse. And in fact, this is the shape we're talking about. Now, you can see we've cut the surface parallel to the xy plane already. There are some of the ellipses. And of course, we've cut it here and down here. And you should really imagine the whole surface carrying on upwards and downwards. And in fact, the further we go from the xy plane with our section, well, the larger the ellipse we'll get. Okay, so we know all about sections in these planes, but what of a section in a vertical plane? For example, what about a section parallel to the YZ plane? Well, parallel to the YZ plane means a constant value of x. So let's put x equals k into the equation, and rearranging we get this. And of course that looks like the equation of a hyperbola, but there are three cases to consider. You see, 1 minus 3k squared can be positive. That's when k is pretty small, so we're actually very close to the YZ plane. And then we get a hyperbola like this. Now if we move slightly further away, increase k a little bit, so that 1 minus 3k squared is 0, in that case we just get a pair of straight lines. And moving still further away, that's for large values of k, well again we get a hyperbola, but this time you see it's the other way up. Well, let's see that on the models. Here's the shape again, and here's a plane for a very small value of k. In fact, it's the YZ plane. If I actually cut the model and remove half of it, then I think you can see it really is a hyperbola. And now if we increase k slightly, so that the plane is now a little bit further from the YZ plane, and again cut the model, then I think you can see we get a pair of straight lines. And moving still further away, so this plane is actually quite some distance from the YZ plane. Well, as we expect, we get a hyperbola, and it's the other way up. Well, we call shapes like this, whose equations have, first of all, a positive constant, and then two positive coefficients and one negative coefficient, we call shapes like that hyperboloids. And I bet you've seen a hyperboloid before, even though you may not realize it.
Well, what you've just seen is a special case of a hyperboloid with a circular section. Now, what I want to do is carry on David's work where he's looking at the various possibilities for the coefficients. Well, we've seen when they're all positive, we get a nice ellipsoid, and David's just looked at the case where I have one negative, and there he got hyperboloid. Now, what happens if I have one coefficient positive and two negative, say -2 and -3? Well, we can see what happens by our old method of sectioning. Let's take an x equals k section and rearrange the equation. And what do we get? Well, in the right-hand side, we have something which might well be positive, and if it is, of course, we'll get an ellipse. So let's see what that looks like in terms of this rather pretty model. Well, here are my x equals k sections, and as you can see, they're very nice ellipses. But what's happening in here? I've got nothing at all. Well, that happens for the values of k for which the right-hand side is negative. I'm not going to get anything in here. And then I'm going to get my ellipses on the right-hand side again. These two pieces go on forever, but the first thing to notice is that this is a surface which splits up into two pieces. Now, what about other sections? Z equals constant, parallel to the xy. Well, it doesn't take much imagination to realize what you're going to get. It's going to be a curve, a conic section, which splits up into two bits. And you realize that's going to be a hyperbola. And similarly, if we take the y equal constant sections, then you can see that we're going to get a hyperbola as well. In fact, we've just taken one dissection for you, and you can see the very pretty hyperbola that we get. We'll get a whole family of hyperbolas like that. Well, let's see what we've done. This last quadric surface that I've had got hyperbolas in sections, and we call it a hyperboloid as well. But to distinguish it from David's hyperboloid, which was in one piece, we'll call his a single sheet or a one-sheet hyperboloid, and we'll call mine a double sheet or a two-sheet hyperboloid. And I think with that, we've pretty well exhausted all the possibilities. Well, not quite. I suppose I should have the case where A, B, and C are all negative. But that would make the left-hand side negative and the right-hand side positive, and that would be nonsense. There's no such real quadric surface. So we've really exhausted all the possibilities for positive or negative coefficients. Now, let's go over these possibilities again, including the cases when some of the coefficients can actually be zero.
We started with an ellipsoid defined by elliptical sections in any plane. The equation in standard form has all its coefficients positive. Now look at the effect of changing the z coefficient. As it approaches zero, the ellipsoid becomes increasingly elongated in that direction. At zero, that is, the equation is independent of z, we have a surface we call an elliptic cylinder. Now, if the coefficient of z becomes negative, then the surface becomes a hyperboloid of one sheet. We now have an equation in standard form with two positive and one negative coefficients. Now, by reducing the coefficient of y, we'll eventually end up with two negative coefficients, but on the way, the equation will become independent of y, and that means the section for any value of y is the same hyperbola. The surface is described as a hyperbolic cylinder. But then the coefficient of y becomes non-zero again, this time negative, and then the surface becomes a two-sheet hyperboloid. Well, in the animation we saw a whole family of quadric surfaces. First the ellipsoid, then the elliptical cylinder, the one-sheeted hyperboloid, then the hyperbolic cylinder, and we finished with the two-sheeted hyperboloid. Well, all these quadrics are what's called central, and these are the most interesting ones. There are one or two more, and those are dealt with in the text, but mostly they're rather special cases. And in fact, two of these are a little bit special. For example, if you look at the elliptical cylinder, and you'll notice that all the slices we've taken parallel to the xy plane give the same ellipse. So this cylinder is obtained by just sliding an ellipse up and down the z-axis. And the equation of this cylinder doesn't contain z. So that really is rather a special case. And also, the hyperbolic cylinder, when we slice this parallel to the xz plane, we always get the same hyperbola. So this cylinder is obtained by just sliding a hyperbola up and down the y-axis. And again, the equation for this doesn't contain y. So that's rather a special case. Well, all these quadric surfaces are ones whose equation can be reduced to this standard form. And in order to do that, we have to be able to get rid of the linear terms. But that isn't always possible.
Now, equations which can't be reduced to the standard form ax squared plus by squared plus cz squared equals constant, they're called non-central quadrics. And this is what happens. When you try to diagonalize your symmetric matrix, well, you can do it all right, but you'll find you've got some zeros along the diagonal. Here we've just put in 1 0. Now, the presence of that 0 will, in general, prevent you from getting rid of the linear terms. So, in this case, what we get is something like ax squared plus by squared plus some linear term in z equals constant. And this is what that looks like. Well, we can actually simplify this slightly by a z translation, like so. And that will simplify to this form, which we can take as our standard form for a non-central quadric. Well, what sort of animal is this? Or rather, what sort of animals? Because what we have to do now is to look at the various possibilities for the coefficients a, b, and c. Well, we might as well take the coefficient of z to be positive, and negative z will simply reflect the surface that we had in the xy plane. So we'll take that as positive. And let's look at the case when a and b are positive too. So we'll take a, b, and c positive numbers. So this is the case where a is 3, b is 2, and the coefficient of z is 8. And we can see what sort of surface this is by our technique of sectioning. So let's take the section x equals 0. That's a very simple one. And when we do that, we see that we've got a familiar equation. Well, it ought to be. It's the equation for a parabola. So we see that the x equals 0 section gives us a parabola. Now, if we put y equals 0 similarly, that just blocks that out, and I just get x squared is equal to a constant times z. That's another parabola. So much for the x and y sections. Now, what about a section parallel to the xy plane? If we put z equals constant, then the equation becomes the equation of an ellipse. Well, at least if the right-hand side is positive. And so we see that sections parallel to the xy plane will be ellipses. And we have a model of such a surface here. When we take sections parallel to the xy plane, that's z equals constant, what we get is a series of ellipses. Now, if we take a perpendicular section here or here, then what in fact we get is a parabola. And here we see an example of such a parabola. So for this surface, sections here are ellipses, but sections in the perpendicular directions are parabolas, and it's called an elliptic paraboloid.
Well, that was when both the coefficients a and b were positive. Let's try and see what happens when one of them is negative. In fact, we get this curious saddle-shaped surface. Now, it's quite a complicated surface, and it's worth some explanation. The equation of this one is 3x squared minus 2y squared equals 8z. If you put x equals 0, you can see you'll get a parabola. And similarly, if you put y equals 0, you'll also get a parabola. Well, let's look at that on the model. You see, here's x equals 0, it's the yz plane, and this black curve is in fact a parabola. If I slice with any plane parallel to the yz plane, then I'll also get a parabola, and here we've drawn one on the model so that you can see it. And of course, if I slice in the xz plane, I'll get more parabolas. Well, so much for vertical sections. What about horizontal sections? Well, of course, horizontal means constant value of z. So let's put z equals k into the equation, and we get this. Now, once again, it looks as if it's going to be a hyperbola, but it depends really on the value of k. You see, if k is positive, that means we're above the xy plane. We get a hyperbola like this. If k is 0 and we actually cut with the xy plane, we just get a pair of straight lines. But if we cut below the xy plane, we get a hyperbola, and it's the other way up. So let's have a look at that on the models. Here we're cutting above the xy plane, and I think you can see quite clearly that it is a hyperbola. If we cut with the xy plane, then indeed we get a pair of straight lines, and if we go a little bit lower, below the xy plane, sure enough, the hyperbola is the other way round. Well, with parabolas this way and hyperbolas that way, we call this surface a hyperbolic paraboloid. It's a fascinating surface, and it's even caught the attention of some architects. The roof of this swimming pool consists of pieces of 4 hyperbolic paraboloids. Here are 2 of them under construction. From the inside, you can see quite clearly some of the parabolas which line the surface.
Well, from that Hatfield swimming pool to the general equation of the second degree is just one small step for a mathematician. And as we've seen in the program, this equation can represent a variety of surfaces, from the central quadrics, such as the ellipsoid and the hyperboloids, to non-central quadrics, such as the elliptic and the hyperbolic paraboloids. Well, you're probably asking, is there some simple test that I can apply straight away to see what sort of quadric surface I've got? Well, it's not all that straightforward, but the first thing you ought to do is to write down the matrix of coefficients and test and see whether it's non-singular. If it's non-singular, if the determinant is non-zero, then you know immediately that you've got a central quadric. But if it's singular, that means that one of the diagonal terms, when you diagonalize, is going to vanish, one or more. And then you have to do a little bit of further analysis. But that's just the sort of analysis that you'll find in this week's correspondence text.